our first talk for the day. So let's see you again. We're going to speak about
Kahler stability.
Kahler stability.
It's I'll talk about progress. It's many years long this progress which is no end, right? Our discussions with Fabian Hayden, Ludmila Tsarkov, and Pranav Pandit. I think Ludmila will give some kind of companion talk because the subject is growing. It doesn't fill to 1 hour now, but yeah. So, what is all about? I recall this. Everybody knows, but still I have to recall Bridge stability. And for this you need cells-thick, you need triangulated category. You need a central charge, which map from K group to C. But for schematics, it's a complete structure. It's completely irrelevant. What is relevant? It's in fact it's oriented two-dimensional real space. It's there's a rule. It's additive map, and then but let's use still complex numbers for any real number theta, which can be thought as argument. We get a class of objects, of semi-stable objects with slope theta, which I know C is stable in C, and satisfies a bunch of axioms. So that, for example, if object is semi-stable, then the central charge is not 0, and in fact has argument theta. And if you shift theta by pi, you get the same thing shifted by 1. Oops, sorry. If theta 1 is bigger than theta 2, and you have objects of slope theta 1 and theta 2, then on E1, E2 is 0. And finally, this main axiom, the existence and in fact uniqueness of Harder-Narasimhan filtration. For any object E, there exists some finite positive integer E and sequence of morphisms, and also some angles which are strictly decreasing, such that cone of E minus 1 to pi is semi-stable slope theta. Yeah, so it's kind of wonderful system of axioms, and then I think it's locally, if you fix category, the deformations are roughly finitely many parameters and it goes through some rank group. So you just change central charge and you do these things. And there are some kind of there are some natural assumptions which are not in axioms but kind of appear in all real life examples. Kind of assumptions are that, first of all, Hom groups between any two objects are finite dimensional maps. It's a category of some field K, and Hom groups are finite dimensional. And also, if you consider in this situation, you can consider stable object, polystable object within the charge, and you consider modular space of polystable objects is given central charge and given theta. R, which is absolute value of Z, the length of this charge. Then this moduli space should be, let's say, algebraic space of finite type. Or if you do some analytic geometry, should be analytic space of analytic if K is complex numbers or non-Archimedean. Central charge of E, which will be central charge of E will be exponent of E type. So you get what you get in the stationary, and also there's some kind of support property which applies these numbers for stable objects form discrete subset of complex numbers. You get polystable. It's a sum of stables, and stable is the object which doesn't have fits and triangle. Yeah, it's like in any equations. This subject. It's only one definition. Okay. So you get infinite collection of more and more complicated kind of schemes or algebraic spaces, strictly or analytic spaces, some kind of finite dimensional varieties, more and more complicated. And it's whole thing depends on finite many parameters, so it's a nice cute object. And what are examples of such things? Yeah, so the first two examples will be kind of fictitious examples, but what was really original of the subject, the first example is D-Branes. So it's not mathematics yet. It's kind of, it's all came from inspiration by Mark Douglas. If you have whatever n equal to 2 superconformal field theory, yeah, it's still mathematical objects. One can try to speak about boundary kind of supersymmetric boundary extensions, boundary conditions, and they should, yeah, it's something which there's A or B or model twists, so there are two categories around, and this when you get this unitary boundary conditions, it should be polystable objects. In corresponding to categories. Should be, yeah, it's all. This supersymmetric D-Branes, what this is called, should be a polystable object. Yeah, but we have really little things as mathematicians to say about it, yeah, just okay. And yeah, so Douglas extracted some axioms and then Bridgeland kind of put it in more mathematical form. You see that this story depends on two parameters, A model and B model parameters. And if you go A model parameters goes to model parameters go to infinity, but B models parameters are fixed. Then one gets something a bit more mathematical, namely the following. So it was example 2, continuation. One can make the following optimistic prediction. Suppose I get a, let's say, compact symplectic manifold. And also it will have a complex structure. In fact, it will be Kahler manifold. So it has some complex structure. And it will have holomorphic volume form. Yeah, so it looks like Calabi-Yau, but it's not Calabi-Yau-metric. I do not insist on the condition that Ricci curvature is equal to 0. So it means that I consider Calabi-Yau variety and put not Calabi-Yau-metric. Yeah, that's a really important point for me. I put not Calabi-Yau-metric, so it doesn't really build a particular example of physics story, so the generalization of physics story. And the category which I have here, it will be Foucault category of X small omega, and with the grading coming from capital omega. And what does at least stable and Foucault category? So what do I mean by Foucault category? So it's like in my here I mean the following. I consider singular Lagrangians sitting in X, together with the lift of argument of omega to real valued function. So I lift to R valued function, at least on smooth part of my manifold. But for Lagrangian it's very singular. And then I put a finite dimensional representation of corresponding wrapped algebra. Yeah, on each smooth component, yeah, on L smooth. Then I can see the finite dimensional representation of wrapped algebra and over a Novikov field, over ring of integers of Novikov field, equal positive. And then I should put some kind of bounded chain also with coefficients in this. Yeah, actually, or maybe I just consider finite dimensional representation over C, and I put bounded chain, kind of like deformation over positive powers, small parameters. Yeah, so it's pretty heavy object, this C, and this I can try to think it's actually as later as metrized objects. Yeah, this form category, but this concrete representations in one can think an analogy geometry like bundle with Hermitian metric and stable objects. Sorry? How L is embedded in X. It's actually embedded not up to Hamiltonian isotopy.
Yeah.
Oh yeah, okay, yeah. Just check. Okay, yeah, okay. You have this algebra like group algebra or fundamental group and consider finite dimensional representation. You can say more. But then it's deformed, so I deform the object of the whole story. And semi-stable objects are special Lagrangians. On each smooth part, the argument is constant.
Can you say just a little bit about the deformation? I didn't understand the previous solution. How we get to deformation?
No. What I said in my yesterday talk, if you get singular Lagrangian embedded in ambient symplectic manifold, there will be certain canonical deformation of this DG algebra, up to gauge equivalence. And I consider kind of representation of this deformity. Okay.
You won't say how we.
Oh, it's based on homomorphic. It's some machinery which we don't care about. Yeah, and semi-stable objects are special Lagrangians. So it means that omega restricted to L is 0, it's Lagrangian, but also imaginary part of exponent minus E theta capital omega restricted to L is also 0. Yeah. So it satisfies two equations. No conditions of singularity. Yeah. Yeah, that's we can hope it will be a kind of real mathematical example of stability condition, but we're very far from it. There is still another example which we really know when stability exists. It's representation of a quiver. You have some quiver. And consider path algebra of quiver, and associate to each vertex of the quiver an arbitrary complex number with positive imaginary part. Then the claim that if you consider finite complexes of finite dimensional representations, or DB with finite dimensional homology of KQ models, has stability structure, and it will have stability structure give it T structure, some abelian subcategory. You can see the object built from things theta running through some half plane, and you can see the upper half plane. It will be just a representation of quiver in vector space in degree 0, and this numbers gives notion of a slope, and you define stable object as object which don't have subobject with larger slope. Yeah, so this spaces will come automatically from this description. We will get T structure and central charge. automatically all this thing. And yeah, of course, people. It's essentially only solid case where you know stability. One have a little bit of generalization. Consider maybe quivers with relations, but it's just the same story. And of course, people in kind of trying to do Thomson invariance and so on, they succeeded to do something for coherent sheaves on varieties up to dimension 3, and that's a natural bound for techniques. I think that's dimension 4 will be pretty hard to use traditional break geometry. Yeah, but these are two groups of examples. So the first example I kind of forget because it's not mathematics. One can try actually combine examples 2 and 3. No, not yet. It's just talking about stability. Okay. I'm talking about stability.
2 is not stability yet.
Sorry?
2 is not.
It's not mathematics yet. Yeah. No. It's a definition.
Yes, but it's not.
It's not nobody checked that it satisfies semantics. Yeah. No. But the definition is, but it's really full description of what is stable, semi-stable objects. And yeah. So in a sense, it's a definition, but you don't have to prove that it satisfies axioms. Like some min curvature law. Yes. Yeah, I gave a definition. Yeah. No, this is a definition. Yeah. No, it's nothing's wrong. But how one can combine together? There was this kind of very general idea of kind of Kahler collapse in the game, and in particular, one should do something like Foucault category with coefficients. And coefficients, some long story what are coefficients, but one can make kind of some very particular case. Suppose x omega is elliptic curve. Yeah, so so it's elliptic curve. C mod z plus tau z. Right, elliptic curve, which has holomorphic Poling form, which dz on c. Yeah, it's not part of the story, so we forget temporarily about dz, but and omega will be some function times dz bar I. Where rho is arbitrary positive function on a torus. Yeah, so you get symplectic structure on two-dimensional torus and some complex structure which will play later some role. And I want to make kind of tensor product of x Foucault category, completed tensor product, by some auxiliary category C0, where C0 will be over some field K0, will be a triangulated category plus its own stability structure. C0, which it's not a 0. Yeah, suppose I get just some any category stability structure, which I can say Foucault category of some manifold, and I want to multiply this manifold by this Kahler manifold. And what will be objects of these categories? Objects will be the following gadgets. You take your curve of the tensor product, yeah. And also maybe a second of what will be metrized object of the tensor product. At least some metrized object of the tensor product. It will be the following guys. You have your torus, and then you start to draw some graph on it. Some graph on a torus. Graph G, then you choose also argument of this form omega 1 restricted to edges of G, maybe an R-valued function. Also, for each edge, you get objects of your category C0. And then at vertex, when you get vertex of the graph, you get bunch of objects from left, bunch of objects, and this should form.
So argument is fixed.
On H is fixed, yeah. And then with appropriate shifts, this object should form representations of Quiver A d minus 1, where d is the degree of the vertex. And then you should add boundary constraint, which is kind of black box, using this holomorphic disks on a torus. And what you get this category over Novikov ring, which will denote by K, which will be kind of Novikov ring with coefficients in A0.
How do you use argument, not just any object is zero, but this, how the argument relates to the object?
Yeah, no, I think when you approach these things, you get also natural argument, you take difference, you get integer number, you shift this object by these integers. Yeah, on H I have argument and object, but these things up to some changes. For example, object I can shift by 1 and argument shift by pi. And when I approach the vertex, I have canonical choice of argument, so I have canonical choice of objects. Yeah. No, it's just objects of the category.
So the object has no relation to argument. So.
No, it's two independent things, yeah.
So the representation is the home of the objects?
Sorry?
Is it the formal representation of three?
Yeah, locally you get something like 6 objects and they form, or maybe 3 objects if it's 3-valent vertex, and they form kind of exact triangle. Yeah. And then you should add something boundary constraint, which is complicated black box, which I don't want in positive power of small parameter.
Is it black box even in the case verifical?
Sorry?
Is the black box even in the case verifical?
Yes, even in the case of elliptic curve, yeah.
From a disk is very much trivial.
Yes, yeah, but to write, we are not yet ready to present explicit formulas.
So object on H is not semi-stable.
No, nothing is semi-stable. And the semi-stable objects in the tensor categories, in this tensor category, will be the following. One, so first of all, objects will be semi-stables. Object on H belongs to semi-stable. Edges are straight with respect to omega 1, 0. In this flat structure, so it will be completely straight polygons, and argument of objects, maybe object ER, whatever, EH, plus argument of omega 1, 0 on the edge. To the complex structure, to kind of flat metric, maybe you get flat metric as well. No, it's not Kahler metric. Flat with respect to this. Yeah. And arguments, if you add argument both from restriction of one form and of object, you get the same constant theta for all vertices. Yeah, so that's kind of more clean picture than we have in general symplectic manifold, because the singular Lagrangians are very kind of simple geometric objects. Yeah. Besides this black box of boundary condition, yeah, this looks like a very solid mathematical definition. Yeah, but we are still not ready to claim that.
You didn't say how the boundary constraint is affected by the stability condition.
No relation whatsoever. That's the
No
point.
condition.
No condition boundary constraint. Yeah, that's the point. Yeah. Yeah, and yeah, so it's. So this big theorem should be that somehow from Bridgerton axiomatics on category C0, you should get Bridgerton axiomatics on the new tensor product. And this actually will be very cute because, I already gave a talk a few years ago that from this by induction, one can construct stability structure on derived boundary category coherent shifts on multi-dimensional abelian varieties, which will be product of elliptic curves, kind of Tate elliptic curve, because you divide by area. It's not this elliptic curve, but kind of elliptic curve of arbitrary dimension, and stability condition will be very far from the custom modular space. It will be described by complex structure on product of some abelian variety, which is not degenerating, product of complex elliptic curves.
So completion means you take equilibrium.
Completion.
Yeah.
Completion. Because it's something. I want something of a non-Archimedean field. It's already kind of here. There's maybe for K-category kind of over Z, from parts using Z. Yeah. Yeah, so that's kind of future mirror situation. So in principle, we're really happy to do this mirror symmetry with coefficients and the basis just complex fund dimension. It's already a very rich example and produce a lot of things. Yeah. Yeah, so we get this combined situation. For example, we can take Quiver or by induction for this situation. Produce new fields, a category of new Novikov fields. So what happens in all this situation? Yeah?
If you had like a symplectic manifold fiber of the elliptic curve,
Huh?
if you had a symplectic manifold
Yeah.
fiber of the elliptic curve, is it here you get something smaller?
Yes. No. In general, if suppose you have Kahler manifold which maps to curve, like elliptic curve, and fibers are Calabi-Yau, its total space is Calabi-Yau, but even could have singular fibers that will be named as coefficients will be not local system but constructible shifts. Yeah, this whole story will be has a huge generalization and get also singularities.
This was just a plain product situation.
It's just plain product situation already very rich. Yeah. The central charge you integrate. If you get this Lagrangian manifold, you sum over all edges. You get central charge of the corresponding object, and multiply by integral of omega 1 0 over the edge. No, but then this question says it's a zero object.
So the central charge is some complicated function of theta.
No, central charge is for the object.
Yeah. It depends on the object, but also depends on theta, which is some.
No. For this object, the central charge will have argument theta. You can say the theta is semi-stable. Objects, it's a definition. Yeah, so there are these three groups, various examples. And then there is some kind of very general argument, general remark. If we forget about examples, just do bridges axiomatics. Suppose we get category with central charge and semi-stable objects and so on. Yeah, so we get category with stability. Then we get for any theta and r, we get a modular space of theta polystable objects and such that central charge of objects will be r times e theta. So you get some modular space which depends on this complex number, and as explained, kind of naturally assume that it's kind of analytic or algebraic space. And in fact, even in simple cases for quivers, it's not a scheme in general, because when you divide by isomorphism classes, you don't have, you get something like Kazuma algebras naturally from the game. You get some plus and Brouwer group, and yeah, it will be no natural notion of functions in this case. Sorry? Because you take quotient, you can take quotient of some variety by some group, and in principle, you shouldn't expect it to be. Not stacks. Yeah, it's called gerbs. Yeah, so gerb story here. Okay, but what I want to say on this space, one has natural class in Néron-Severi group tensored by MZ, tensored by R. Get natural kind of class. What is this class? It's how to explain this second cohomology, last and second cohomology group. Yes, it's actually it indicates that something is missing in Bridger-Decker semantics, which we should probably add.
Wait, MZ, what is MZ again?
Modular space of polystable objects. Yeah, it's actual Hausdorff things. Yeah, this guy actually, if you consider the case of quivers, it could be kind of essentially projective variety, or could be not projective. If quiver has loops, then it can have a trace of the loop. It's kind of actual function, so it projects on some affine space, but fibers are projective, so it's kind of mixture of affine and projective variety. What is this class here? It comes from the following story. Suppose I have a central charge from my category to complex numbers, an additive map. And in real life situation, it goes through some finite dimensional quotient. Go to some Z or N. See? So it means you get many maps to integers and then take linear combination of these maps. How to map K0 of category to integer number? You calculate earlier characteristic of some complex. So what you can imagine is that you get some functors, it's a kind of functors on my category to finite dimensional complexes. Some triangulated functors. And they'll also get some numbers, Z1, Zn, which are arbitrary complex numbers. And the central charge will be sum over Zi, earlier characteristic of Pi. Yeah, like if you consider representation quiver, consider space of representation given a vertex. And it will be a generalization of this story. But if you consider, I don't know, some coherent shifts on some variety, you should have functional on kind of integer cohomology. But one can realize its classes in integer cohomology, and it can represent, if it's algebraic classes, by earlier characteristic X come from some other objects. Yeah, so it's a pretty natural assumption. But if you raise S6, then we get line bundles on the stack of objects, namely bundles of Li. Li, this stocked object E, which will be defined as determinant of this complex. And central charge, what is and then one can take and take tensor product of, you take kind of absolute value of the things if you have single complex numbers to, just a second. And this things gives gives you line bundle on the stack of objects, and now I take tensor product of Eli and raised to the power imaginary part of exponent minus, and I put square root of minus 1 sub Ci. You get some virtual
I of E.
yeah. You consider this tensor product of kind of real linear combination Néron-Severi group, and it's again virtual line bundle on stack of object, but easy to see the dilations of objects act trivially on this. If you dilate because of consideration things, yeah. In fact, this if you consider dilation group of object, kind of like Jm acting on an object, it acts on this line bundle by multiplication by earlier characteristic of Pi of E. because rescaling goes to rescaling and determinant. Yeah, and then because the imaginary part eventually cancels, you see that rescaling acts trivially, and more generally for polystable group object automorphism group acts trivially in things, you get well-defined virtual line bundle. And the observation is that this class is non-negative. So if you restrict to any curve, you get automatically non-negative number. Yeah, so this one can kind of cook up the argument. Namely, if you have some curve S, which maps to this MZ, S, curve S. Yeah, so does it mean curve maps to the moduli space? You get a family of objects parameterized by this curve, semi-stable objects, and then again, it's not really part of semantics, but should work in the global case. Then one should get a global object, kind of R gamma of this holomorphic bundle of, say, representation of quiver. Suppose you have a representation of quiver, depending on parameter space. Then on the curve you get family of representation. Take R gamma, get again some element in representation of quiver. Yeah, so you get this guy, which belongs to again category, and it's easy to see that suppose all ES are CT semi-stable. Then if consider theta prime, which is for any theta prime bigger than S, and for any E prime, which is theta prime semi-stable, home from E prime to E global is 0. How calculated, you consider R home from E prime to E global, it will be R gamma of space of homes, and this will think is in positive degrees. So R gamma will be still in positive degrees. So we get it automatically. And similarly for any C. Yes? Yeah, yes, because moduli space they know that it's all semi-stable objects. Yes, the same theta, yeah.
This is another curve.
No. No, this is curve, yeah. This one.
Z, do you fix theta?
Of course, Z is argument of theta, yeah. It's,
What means for any theta prime bigger?
for any theta prime, and for any object in a object home to this global is 0, and it's similar for any theta less than theta minus pi. And for any kind of semi-stable objects, theta double prime, home in opposite direction are 0. By similar arguments, because you get now locally home groups which sits in negative degrees, and then we get less than -1, and then you take our gamma get 0.
Do you need something about these functions phi I in order for that to be a line bundle?
Sorry?
Do you need some conditions on the phi I in order to actually be a line bundle?
Nothing. Just this definition, determinant is the legend.
Which very nicely, it just is very
How's the determinant?
Sorry? The determinant of a complex. You have finite. You get bounded complex finite-dimensional space. You take product determinants and alternating power.
What are the natural symmetries in this situation? It seems that if you fix the collection of phi i's, you not only get a real line bundle, and it's very classic, but you actually get
actual bundle.
Actual bundle with parabolic expansion, with divisors, fractional divisors, actual divisors, because you can take not just the Euler, not the determinants, but also the jumping forward.
Oh no! I don't reach essentials.
So it's not only part of
No, not at all. Yeah. And in fact, even this line bundles are irrelevant. The final story, but we did some kind of small enhancement of central charge.
They seem to be relevant here in this.
Yeah, no. It just kind of it's this argument. Here gives in this situation I really need them. Yeah, and from this follows that this E global built from object, stake only in half plane, and then I take imaginary part to get positive number, and this imaginary part gives you, by some kind of Riemann-Roch theorem, gives this positivity of this class. Yeah, so it's kind of it's heuristic argument. One needs kind of adjust definitions and to make it work, but it's kind of convincing in real life situation. So you get non-negative class, and now if my field is kind of complex numbers or non-Archimedean, one can ask whether its class comes from Kahler metric, maybe on a non-compact variety, because the fluid has loops, it's non-compact. So it will be quasi-projective variety, roughly, if it's scalar. Kahler metric. And so the rough idea is that what is scalar stability, it's something which we still do not know on triangulated category defined over field over which Archimedean or non-Archimedean. So it's really analytic geometry, which produce Kahler metrics on all modular spaces of polystable objects simultaneously. It's some kind of structure in the category which produces Kahler metrics. And how it fits with the whole story. Just before going on, I want to say a few words what are Kahler or semi-positive Kahler metrics in non-Archimedean geometry. Yeah. First of all, let's return to complex geometry over complex numbers. Suppose I have M, which will be some analytic space. Yeah. If it's smooth, one can speak about pluri-subharmonic functions. Sign change functions. They form a sheaf on my manifold of additive monoids. You can add pluri-subharmonic functions. So the equations means that you get a function, take something d bar, take this non-negative 1-1 form, or you can take kind of completion, get non-negative 1-1 current. This 1-1 current. Functions, for example, I can try to see. It could be pretty singular, but for continuous functions, things is well defined. Function C0. In all examples which we will have later, functions are really in C0, don't have Worth singularities. And the same, and this pluri-subharmonic function can be written as a limit, kind of positive linear combinations, limit of positive linear combination of functions of the following things. It's locally. You consider logarithms of pluriharmonic functions, which are logarithms square of the invertible harmonic function. But you take not with and also you take maxima. Yeah, because these things will be pluriharmonic. So pluriharmonic functions is functions which are so that the second derivative is 0, this intersection, it's a sheaf of abelian group. Abelian groups. And a virtual line bundle can be defined. It's a torsor of this sheaf of abelian group. And then one can speak about non-negative metrization of the things that's if you locally trivialize, you should choose pluri-subharmonic function, kind of metrized, non-negatively metrized bundles, the zero section of the quotient. Right? Yeah, and the same definition one can use in. It's non-negative 1-1 currents. Can be thought as sections of this sheaf. Yeah, matrix. And in non-Archimedean geometry, one can develop the same story. It will be Berkovich spectrum. So what really goes in non-Archimedean geometry? if over non-Archimedean field, if you have some variety, then we get kind of model over the ring of integers. And you choose a model, and when you choose a model, let's suppose it's discrete relation, you get some kind of special fibers will be consist of many components, and that can make kind of polytope elements, polytope, dual polytope. In the case of first will be a graph, in high dimension case it will be some simplicial complex. It's a simplicial complex, and Berkovich spectrum maps to this complex. And then pluriharmonic function, so part of pluriharmonic function will be something like convex functions on the polytopes, and at vertices the condition will be in some positivity in neuron severity group. And if you get this pluriharmonic function, convex function, so now kind of write this real inequality, then the second derivative gives a metric, maybe degenerate metric on the base, and you can imagine that it's a Berkovich spectrum project to this guy. This has a metric which could be degenerate in some direction, so it again shrink to something smaller, and you get mapped to some metric space, so you get kind of degenerate metrics. Some distances are zero, it collapses to small dimension 6. Yeah.
Why did it collapse?
Because in fact, the Berkovich spectrum project to it, so along the fiber the metric is zero. Yeah, so many points are glued together, and eventually get some kind of compact space with a metric, but small dimension.
So the way you get
If it's plurisubharmonic function, yeah, so it means that in simplices you get convex function, and second derivative gives you a metric. Again, one needs some regularity. Okay. Yeah. So there is this whole story, and this can be thought as kind of limits. Non-Archimedean field we consider like one parameter families of complex varieties, and if you have families of Kahler metrics, they can collapse in a nice way, and you get non-Archimedean Kahler metric. Let's describe this story. So there is some. Yeah. I'm talking here. It's a talk, yeah. Yeah, and yeah, and there is this Calabi conjecture, and yeah, this whole story around this.
Which Calabi doesn't make sense for this thing?
Sorry?
Which Calabi doesn't make
Yes, 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 and actually people proved Calabi conjectures as Buxom, Johnson, and Haber proved it maybe 3-4 years ago. Yeah, so there's everything is here. Or on some, if you choose choose model and choose a metric and camera spectrum, it gives example of metric on such. Okay. Okay. So this is notion of Kahler metric in non-Archimedean case, and now I want to say this.
So since the beginning of the talk, I never understood this metrized word that came out.
Metrized? Okay, yeah.
Like what does it really mean?
Yeah, let me just go to. Yeah, no, one should go to example. Why should it metrized? Here.
Yeah, here and before.
We can see the metrized line bundles is non-negative.
It's just a metric.
Metric on line bundle.
Yeah.
Metrized line bundle. Yeah. With non-negative curvature.
So what's the relationship between each one and each zero?
This is a map from which one to zero. Boundary map. If you get Kahler metric in this, then you get a scalar class. It's considered Kahler metric. It's scalar class. So there's a huge infinite dimensional space of Kahler metrics in this expanded dimension. Okay. So now, when we should expect the scalar metric? So again, in physics example, this n equal to 2 superconformal field theory, there is something called Zamalotchik metric on the space of model space of D-Branes, and it's assumed to be, I think it's, people believe it's scalar metric and it has the right homology class. So So that's origin of all this Kahler structure in string theory. Yeah, no, because when you deform these boundary conditions given by some local observable and then get Hilbert space structure. Yeah, yeah. So it's better not to talk about it. Yeah, yeah, yeah. Then if you consider Foucault category, when you get variety with volume element, but not Ricci is not flat, not 0 S form. That's when the homology class of Ricci is 0. Why you get? I claim you get kind of non-Archimedean Kahler metric, and the reason is following. Suppose what I have a Lagrangian variety, which will be special Lagrangian. Yeah? And when we consider deformations of the special Lagrangians, they are given by if you just move a little bit to get kind of normal vector. If you move normal vector, kind of delta L will be a section of normal bundle. You can pair it with one form, pair with symplectic form, and you get a closed one form on L. So it means the tangent space to special Lagrangians maps to H1 first homology group of L with real coefficients. But also you can put not omega, but you can also put form which vanish, another form which vanishes on L, which is imaginary part. Put imaginary part of exponent minus e theta omega. Then you get closed n minus 1 form by nth dimension. So you see that tangent space is identified with two dual spaces. And the pairing, its identification gives bilinear form, which is easy to see. It's symmetric and positive definite. So you get remaining metric on locally on space of deformations. And in the affine structure given by first thing, it will be given by second derivative of convex function. So you get this Kahler metric in non-Archimedean case. So the claim is that the same works. One can put into the game coefficients. No. When I get Foucault category, it's category over non-Archimedean space. It's a category of non-Archimedean space. There's this boundary chain, but then it maps to this space of singular Lagrangians, maybe with multiplicities, which will be some finite dimensional real object. No, it's before. No, because Jan asked me the previous stage, so before he interrupted me. Okay. You get some finite dimensional space of these Lagrangians. When you forget about boundary constraints and so on, it's real finite dimensional real guy, which has remaining metric, which is convex in this fine structure sense. So you kind of take it, pull back, you get degenerate metric on the space of objects, which is, I claim, is a Kahler metric in this situation from capital omega. Because you identify this dual space using capital omega. Yeah.
Is it a frac connection part? Maybe we should
Sorry?
usually couple frac UM connection.
Yeah, it doesn't really matter. Yeah.
Frac that down.
Yeah. I completely ignore this. What I put on here. Yeah, it's kind of non-Archimedean limit. It's not actual complex metrics depending on parameters. Yeah. Yeah. So and there is a third example. When you do quivers. Now I do quivers for complex numbers. It's a representation of pure complex numbers. And one can choose generators, T alpha, kind of from the path algebra, some collection of generators. And then one can write the following thing. One consider imaginary part, exponent phi e theta, of the following guy. You consider sum over z vertex. I remember we have numbers in upper plane multiplied by determinant of HV, which HV will be metrized object will be the following. You consider representation pure, let's say, this Hermitian norm at each vertex. Metrized object. It will be analog of this Lagrangian manifold, will be representations plus Hermitian metrics. I consider only T structure that we can generalize complex story. Yeah, so I get I consider the following expression. You consider determinants, it actually depends on the base, but if it has slope theta, it's well defined. And then take last one, minus sum over all arrows alpha L2 square of L2 norm of T alpha using this connected vertex V1, V2, using HV1, HV2 squared, which you can write something like trace of T alpha if you draw right in coordinates, something like HV2 T alpha Hermitian conjugate at HV1 inverse. Then you want, because you want to calculate Hermitian conjugate. Yeah, I get this expression depending on Kahler metric, and the claim is that this expression is plurisu harmonic function both in objects, in representation, and the metric. Metric we can represent as quotient of GL modulo unitary group, so we pull back some complex variety, so it makes sense to speak plurisu harmonic function in such things according to GL modulo. And it's plurisu harmonic, it's bounded below in when we speak in case with metrics, even only if my representation is semi-stable and achieve minimum semi-stable, yeah? Bounded below. Achieve minimum if it's only polystable, and then you get Kahler potential for Kahler metric for JIT theory. Yeah, the whole thing looks completely parallel, and now maybe Ludmila will talk about, we have whole axiomatic system with a flow analogous of mean curvature flow and so on, which seems to work simultaneously well both in Archimedean and non-Archimedean situation, but it's for Ludmila's talk. Thank you.
2 minutes for quick questions.
Yeah.
So in your Fukaya category of coefficients, the objects seem to be, you suggest some limit of mean curvature flow for Lagrangian.
No, stable objects are kind of a fixed point of some mean curvature.
So, but if I tried to do this with the product of an elliptic curve with itself,
Yes, yes.
I'd have a straight line in one elliptic curve, but a graph in the other. So someone announced.
No, because it's you get graphs on a previous curve you get a graph. On a smaller curve you get a straight line, on this curve you get a graph. Yeah.
So I'm going to think of one of them is big and one of them is small.
Yes. On which you have straight line, closed loop, it will be small. And in general, by iteration, getting a piecewise linear single expression Lagrangian and product of many.
More questions?
So you was discussing fixed complex structure and then a large volume being, right?
Yes, complex structure for A model, yeah. So
Can one say something not in the large volume?
yeah, I think one can really reach all stability, interesting stability structure by the following kind of general idea that here we have, looks like have non-degenerate stability, but very degenerate category, yeah, like Fukaya category, for 9 parameters. But moduli space of objects are kind of some algebraic varieties. And the hope they are defined over integers, we know only the cosmological space, but should get uniform by algebraic continuation and integration. You say that the same varieties everywhere, yeah. So eventually it should give stability for non-trivial boss. No, example 1, it's very special, get Ricci flat metric. It's not Ricci flat metrics and complete. No. But n equal 2 series, it's very special. Yeah.
Okay, let's thank Max again.